Welcome, everyone. We don't have a lot of time, and we have a lot of things to cover. I've been forced to shorten this multiple times, and I've tried to keep the most important parts. So we'll see how it goes. But we'll dive right into it. So when we talk about large language models, we have to have the basics down. So I want to start with the underlying idea of why machine learning works at all. And the absolute basic thing is pattern recognition. And this webinar is called From Notes to Neurons, so you can imagine this will have a musical analogy to it. So think about music. You have recognizable patterns of notes, rhythms, and harmonies that makes a song enjoyable and memorable. And without patterns, you would just have random noise. And to highlight this, I want to show you a song, very short one, which I think is a good example of what it can sound like when it doesn't have any patterns or rhythms. That's enough. I hope everyone can hear it. I'm going to go back to presenting my slides. So yeah, that was not the best song I've heard. I'm sure it's not the best song you've heard either. And it's all about patterns. So just as in music, pattern recognition is the bedrock of machine learning. It is what transforms a cacophony, like this one, what we just heard, of raw data into meaningful insights or actions. And without the ability to recognize these patterns, a machine learning algorithm would be just like a musician randomly hitting keys on a piano. You would produce sound, but you wouldn't really produce music. And just as music theory gives musicians framework for creating harmonious melodies, pattern recognition gives machine learning models a way to understand and make predictions or decisions based on data. So to sum up, recognizing patterns is not just like a nice to have. It is an essential part of how machine learning algorithms operate. And that is why it's such a foundational, or as foundational to machine learning as musical theory is to composition. And just let me briefly walk through some parts of pattern recognition with the, let's start with the intuitive understanding of it. So when we listen to music, we don't just hear isolated notes. We hear melodies, we hear harmonies, rhythms, like patterns that allow us to recognize a particular song or a music style. And similarly, in pattern recognition in machine learning is about identifying these melodies or regularities in data. And what is a pattern? At least in this context, well, in music, a pattern could be a repeated chorus, a recognizable bass line, or a unique sequence of notes that makes a melody memorable. You can all think of some, like your favorite song, and you could hear it in your head based on its pattern. And in machine learning, this could be like a recurring arrangement of variables, specific sequences of words in a text, or certain characteristics of an image. And why does this matter? And through 4 factors here, I'm gonna explain why this matters and how it's used. So the first factor is composition. In music, recognizing patterns like chord progressions allows you to compose new pieces. I'm sure you've all seen this very popular video on YouTube where they walk through a bunch of very famous hits, and they're basically all the same song. In machine learning, pattern recognition allows the algorithm to make new compositions, like that is predictions or decision based on what it has already learned. The second factor is genre identification. And it's pretty basic. It's just like you can identify a jazz song from its unique set of patterns. Machine learning algorithms use features to categorize data. And a feature could be like a melody or a certain chord progression or a riff. The third factor is improv. Just going to check. So improv. Like a jazz musician, they improvise based on known scales and rhythms. Otherwise, it would sound like crap. And similarly, an algorithm can deal with new data by applying learned patterns. This is what you talk about. Well, this is what you call generalization, to be able to generalize based on what I've known so far to recognize something new, but still be able to determine, okay, I kind of know what this is. And the fourth factor is remixing. So maybe everyone, maybe someone has DJed sometime, or at least listened to one. Then you know that DJs, they take existing songs and they alter them, but the songs still have their patterns. So you can still recognize that it's the same song. And in data compression, algorithms just reduce the data size while retaining its essential tune. And in large language models, this is applicable through, just like chords in a song are made up of a bunch of notes that sound good together. Language models recognize which words are likely to appear together in a sentence. So language models recognize the rhythm of sentence structures. That is the pattern of nouns, verbs, and other parts of speech that make a sentence grammatically correct. And when language models generate longer text, they are akin to composing a longer musical piece with a recurring theme. They keep track of the subject, the maintain coherence, and make sure that the melody of the discourse remain consistent. So to sum up, pattern recognition in machine learning is like listening to a complex symphony and understanding each instrument's role, the themes, the variations, and even predicting what note or sequence might come next. It is a central part of how algorithms understand and interact with their world, very much like how we understand our world through the patterns that we observe. And with that, we're going to move on to statistical learning theory, which I love. So, I'm not going to go through all of statistical learning theory because it's quite a big topic. But I'm going to explain why it is important. And I'm going to do that through 4 statistical metrics. The first one is being able to bound the unknowable. So statistical learning theory's real power lies in its ability to provide bounds on the generalization error. It says, in essence, that we cannot guarantee perfection, but we can mathematically assure you that the error will not exceed a certain limit most of the time. Probability and expectations. Statistical learning theory relies heavily on probabilistic bounds. And I would love to dive more into this way deeper. And if you want to discuss statistics, I'm always here. Well, going back to the probabilistic bounds. These bounds do not claim to predict each and every new unseen data point accurately, just like if it has learned to write music. I mean, we have AI models today that can write music, and you show it something completely new. I wouldn't know what that would look like or sound like, but it would be like, with a high probability, it could probably predict what the next note would be or the next chord, but it's not a guarantee. It's only a statistical guarantee. And you present it as, with a 95% probability, the generalization error will be less than a certain value. And now we dive into something that is a little bit more complex. I'm going to try to keep it as simple as I can. But one of the most important metrics in statistical learning theory is the Vapnik-Chervonenkis VC dimension, which measures the complexity of a model. So like the intuition is quite easy to understand. So it's basically a higher VC dimension implies a more flexible complex model, which is, it's going to be better to generalize to new examples, and it's going to be better to recognize what it has already seen. And statistical learning theory provides bounds on this generalization error that take into account this dimension. Effectively saying, if you keep your model this way, your future error is more likely to be small. From a musical perspective, because I totally understand if that was not very intuitive. So imagine you're learning to play an instrument, say the guitar. A lot of people play guitar. Different songs have different levels of complexity, from simple tunes with just a few chords to intricate solos with the rapid finger movements. The VC dimension in this musical context is like the range and the variety of songs that you can play on your guitar without making mistakes. If your VC dimension is low, it's like only being able to play simple nursery rhymes. You've got the basics down, but complex songs are way beyond your skill level. On the other hand, if your VC dimension is high, you can play a wide range of songs, from simple tunes to intricate rock solos. However, there's a catch here. Just because you aim to play complex songs doesn't mean that you should neglect the basics. If you were to solely focus on advanced pieces without mastering fundamental chords, you will probably make mistakes even in simple songs. And in machine learning, this is akin to a model overfitting. It's so geared towards the training data, in this context, complex songs, that it performs really poorly on general data, basic tunes. So in essence, the VC dimension is, in our musical analogy, represents your guitar playing versatility. Like a balanced musician, a machine learning model should aim for a sweet spot in its VC dimension to play both simple and complex tunes accurately. Statistical learning theory also has a theorem called the law of large numbers. And if you have like read any math or you basically, I would be shocked if you hadn't heard of this, if you have done any math. So it's a fundamental principle in both mathematics and probability theory. And it says essentially that the more data points you have, the closer you get to the true underlying distribution of that data. It's basically like the world behaves a certain way, and I have experienced like 30,000 days of it being the same. So there is no reason to assume that it's going to be vastly different from now on or the upcoming week. And why does statistical learning theory work? Despite, I mean, it cannot see into the future, of course, but why does it work anyway? So statistical robustness is the first one. Statistical learning theory's probabilistic bounds do not require the future to be identical to the past, just statistically similar. And that is a big difference. And real-world systems often obey this principle. So while, like I said, SLT cannot see the future, but it offers the next best thing, a mathematically grounded level of confidence about what we can expect, which often turns out to be remarkably accurate. Like I once took a math course, and one of the first things that the teacher said, I think it was the second lecture or so, he said, mathematics works better in the real world than what it should, according to itself. Think about that for a second. With that, I'm going to jump into what we're here for, large language models. So what are they? At a high level, a large language model is a machine learning model which is trained on an expansive corpus of text data. And when we speak of large in this context, we mean both the size of the training data and the complexity of the model architecture. When we talk about the model architecture and its complexity, it is often quantified by the number of parameters it holds. Okay, then you ask, what is a parameter? So going back to the musical analogy, imagine a parameter in a machine learning model as a tuning knob on a musical instrument. The position of each knob influences the final sound produced by the instrument. And similarly, a parameter in a machine learning model influences how a model translates input, in this case, text, into output. For instance, text completion, translation, or something else. And the training of is akin to a big orchestra. So the goal here, the whole goal of training the model and even using it, like the whole goal is to find the best setting for all of these tuning knobs or parameters so that the model produces outputs as close as possible to what is desired. So imagine an orchestra rehearsing a very complex symphony. When they practice, the musicians, they don't get every note right on the first try. The conductor will listen very carefully and then will advise adjustments. Those could be, for instance, like the violins are too loud, or the flutes are coming in too early, and so on. Musicians then fine-tune their instruments and modify their techniques to get closer to the perfect sound. And similarly, during the training process of a large language model, it listens to its own performance by calculating what we call a loss function. And the loss function quantifies how far off its predictions are from the actual desired output. So it's a way to quantify, I meant to go for an A note, but I managed to produce a B note. And it's that difference that the loss function calculates. And here, I'm just going to take a sip. I wanted to dive way more into the math, but I'm afraid I don't have any time for that. I'm going to show you an equation, though. So what is a loss function? Like I said, the loss function is at the heart of a training process for machine learning algorithms. Remove this, and we don't have anything. And like I said, it quantifies how well the model's predictions match the actual data. It's exactly like a conductor's scorecard, quantifying how close the orchestra is to a perfect rendition of a certain symphony. So, very quickly, this is more advanced, and I totally get if this is not intuitive, but please reach out for me or with questions for me afterwards. I would love to talk to you about this. So, imagine now our orchestra has a goal. We want to create a beautiful symphony that perfectly matches a masterpiece created by some legendary composer. And the conductor, he has a checklist that identifies how close the orchestra is to that ideal performance. And similarly, in machine learning, we have a checklist, which is called, well, this is the loss function, that tells us how close our model's output are, what we know is correct based on the historical data that we have. And in mathematical terms, a commonly used loss function for language model is the cross entropy loss, which is shown here. However, this analogy, it's not perfect, because unlike an orchestra, where there may be like dozens of musicians, a large language model has hundreds of millions or even billions of parameters to adjust. It is as you have an orchestra with all of Earth's population, and even that would be quite small, with each musician playing a slightly different tune, and yet they all have to harmonize. The training algorithms make micro adjustments to each of these parameters, or the knobs, based on gradients calculated by a method called backpropagation. I'm not going to go into exactly how that works, but I want you to at least have heard the word and remember it. And this enormous number of parameters is what allows these models to perform a variety of complicated tasks, from understanding context in a sentence to generating human-like responses in a conversation. But the complexity does not stop there. Large language models often involve ensembles or collection of multiple slightly different models working in tandem to make predictions. Think of this as an orchestra where each musician has a slightly different version of a specific instrument, like guitar, and they are each contributing to a final harmonious output. These ensembles can improve the robustness and reliability of predictions, but they also introduce another layer of complexity and computational demands. Now, when it comes to parameters, I want you to appreciate the size here. So let's put this into perspective. A simple language model might have around 1 million parameters. Those are usually used for a specific purpose, and it could be used for like straightforward text completion. Now, when we move into the territory of large language models like ChatGPT or Google BERT, the numbers of parameters explode into the billions. And at least that was my first question when I started to learn about this. Why do we need so many parameters? Well, why couldn't we just have a tenth of them? That would be way quicker to train them. And the answer to that question is that each parameter captures some aspect of the language, like the syntax, the semantics, the context, idioms, and even nuances and tone. And the more parameters we have, the richer and more nuanced the model's understanding of language becomes. And the architecture of these models is meticulously designed to distribute these parameters across various layers and components, each serving a specific role. And some parameters may be responsible for understanding the grammatical structure of a sentence, while others might focus on capturing the sentiment or context. That was it from the loss function. Okay, transformers, because that is what their models are called in our daily language. So here you can see the development or the evolution of these models. The first one came in 2018. And since then, you can see that there have been quite a few, and even more are being developed as we speak. These transformers, like we talked about, are really big models. And apart from a few outliers, the general strategy to achieve better performance is by increasing the number of parameters, like we just talked about. And as you can see, the number of parameters on the y-axis, and then you have time on the x-axis. The most famous ones, like our ChatGPT, like in the middle. And then you have what Microsoft is working on, or yeah, they're actively working on it right now, I think, the Turing NLG model. So, training a model, especially a very large one, requires a large amount of data. And this is where the challenges to large language models come in. It becomes extremely costly in terms of time and computer resources. And this even translates into environmental impact, as you can see in this graph. So like, look at the second bar. This is the average human life CO2 emissions in kilos. And the bar at the bottom is training one model. And that makes it really important for us to share these models. So you have a trained model, and then you have to share it with other people so that they can use it for their own purposes, just like ChatGPT is shared. Now, I wanted to talk about fine-tuning more. I don't have any time for that. I can see that, though. But I'm going to say that you can train a model from scratch. You have like an empty algorithm, and then you fill it with something, and it takes weeks to do it, and it's extremely costly. But fine-tuning is when you take a model that has already been trained for general purposes like ChatGPT, and then you can apply your own data and fine-tune. Like, you still train it, but you do only the fine-tuning on a small data set, and that way it becomes an expert on that small data set, and it's way cheaper than pre-training the model from scratch. So quickly, we're going to discuss the general transformer architecture, like how do these models actually look under the hood? And it's based on two things, actually three, but let's go with two for now. The first one is the encoder, which you have on the left side here, which is the note taker. And what it does is, imagine that you're listening to a song and you want to remember its key parts. You might jot down the main notes or lyrics so that you can recall them later. And the encoder does something similar to this. It listens to the words or data that you give it and makes a sort of like summary that captures the most important parts. And what does the decoder do? Well, the decoder is the composer. So after listening to a song, you might feel inspired to make your own music. The decoder does something similar to this. It takes the summary from the encoder and uses it to create something new, like a sentence or another in another language, or an answer to a question. Then we move on to what actually is very revolutionary when it comes to large language models. It's called the attention layer. And turns out love is not all you need. It's attention. So a key feature of a transformer model, a large language model, is that they are built with special layers. These are called attention layers. And if you want to read about this, there is a paper that was introduced a couple of years back, which is called Attention is All You Need. And the attention layer is what makes the LLM seem magical. In simple terms, the attention mechanism is like a conductor emphasizing particular notes in a symphony to bring out its soul. Just as a poignant chord in a melody guide your feelings, the model accentuates specific words in a sentence. In a ballad of adventures and discoveries, certain terms will resonate more, shaping the essence of the story. In large language model terms, it has read tons of text and has learned which words usually holds more weight in different contexts. So when it sees a new sentence, it knows which words to focus on to either understand the sentence better or to make an accurate prediction about what comes next. And we're going to finish this talk with how you can apply these models. And I'm sure you've all run into this in one setting or another. But still, text generation, it's like composing a new song based on existing melodies and rhythms. Large language models can automatically generate text that mimics human language because it has seen so much of it already. And this is, of course, useful for a wide range of tasks like writing emails, creating chatbots, or generating news articles, or to help write webinars. Question answering. In the context of question answering, think of a large language model as a well-informed librarian who has read every book in the library. And the model can scan its vast repository of knowledge and provide precise answers to your queries, from simple factual questions to more complex inquiries requiring contextual understanding. Text summarization, and for a large language model, and in the musical analogy, it's akin to creating a greatest hits album of a lengthy discourse. You all know what it is. But it's really great in doing this. And sentiment analysis is like deeming what kind of sentiment does this text hold. It's basically like a keen observer of human emotions. It reads through the text and identifies the underlying sentiment, be it happy, sad, angry, or neutral. And it's usually used by businesses who wants to understand customer feedback or for analyzing social media content. And with that, I'm sorry I took that much time, but I hope that you found it interesting. So thank you. You have 1 minute to ask questions.
Thank you so much, Jens. What a boom, 30 minutes in and out, done. And you are completely right. Love is not just what all you need. Attention, all you out there, people need attention. I know some of you might have to run off now and go and get your lunch before you need to head back to work. And this has been recorded, so don't worry, you will be able to catch it all again. And if you do have any questions that you don't have a chance to raise now, then please get in touch. But if there's anyone here that does have any questions right away, then please do stick up your hand right now and we'll get Jens to answer them. Going once.
I would love to find some questions.
Going twice. I actually have a question. And it's probably, I'm not sure, I think it might be a bit of a long one, but you know, I work with marketing, but how do I write efficient prompts?
How about we have a workshop?
Oh, I'd love a little workshop about that.
Yeah, we might have a workshop. I'm very used to using ChatGPT now. I've used it since the first day it came out. I mean, it's like Googling. It's an art. I would say some general feedback to that question would be like, be very, very precise. Don't assume like you do with people that they know stuff or can contextualize. They can, but it's way easier for them to understand if you're precise.
Perfect. Well, then if there aren't any further questions, I'm not going to take anyone else's time. Thank you so much for sharing your knowledge with us today, Jens. Thank you, everyone, for joining us, and keep your eyes open. Oh,
question.
I thought it was a question there. I got so excited.
Yeah, I mean, if I have time, I would ask one question. Mm-hmm. First and foremost, thank you for the presentation. It was really interesting. It could be longer, easily.
Yeah, I think we need like 2 hours.
Yeah, for sure, or a day. So my question actually turns back to, as a software developer, I know there's like a lot of courses, a lot of different material out there that you could like start building on top of that. But what would be your advice as practitioner and someone who has more insights? So where to start and what do you think would be best for a software developer to look into for future use?
You mean in terms of courses or like libraries, languages?
And any resource.
Okay, I would go for Python. I would go for deeplearning.ai. They have excellent courses. I would learn to use TensorFlow, LangChain, Hugging Face, and scikit-learn.
Okay, thank you. Noted.
Good.
Did you really manage to jot those all down in the time it took them to fly out of his
Just
mouth?
reach out to me if you have any questions. I'll be glad to discuss.
I have some notes already, but yeah, I just did the check marks. So yeah, thank you.
Perfect. Well, any other questions? No? Perfect. Well, thank you so much for joining us today. Keep your eyes out for our next webinar. And I hope you have a lovely end of this week.
Thank you, everyone. Have a great time.
Thank you.
Bye.
Bye.